Today we're looking at a common array challenge. Given a list of numbers, can you quickly determine if there's any number n in the list such that its double, 2n, also exists somewhere else in that same list? It's trickier than it sounds, especially when you consider efficiency. The problem asks us to check an array of integers. We need to return true if there are two distinct indices, I and j, such that the element at I is exactly twice the element at j. If no such pair exists, we return false. The core challenge is finding these pairs without excessive computation, especially with potential zeros or negative numbers. The most straightforward approach involves a nested loop. For each number in the array, we iterate through the rest of the array to see if its double exists. This means for every element, we potentially scan the entire array again. While simple to understand, this repeated scanning makes it inefficient. If our array has n elements, this approach takes roughly n times n operations, leading to an n squared time complexity. Space complexity is minimal at big O of 1, constant time because we're not using any extra data structures beyond a few loop variables. The key insight to optimize this is realizing we can check for the existence of a number's double much faster than iterating. If we've already seen all previous numbers, we can store them in a way that allows for constant time lookups. A HashMap is perfect for this. We iterate through the array once. For each number we encounter, say current number, we ask two questions. Does current number divided by 2 already exist in our map? Or, does current number multiplied by 2 already exist? If either is true, we've found our pair and can immediately return true. After these checks, we add the current number to our HashMap to be considered for future elements. This way, we only iterate through the array once, performing quick lookups and insertions. Let's trace this with an example, the array 10, 2, 5, 3. We start with an empty HashMap. First, we process 10. Is 10 halves, which is 5, in the map? No. Is 10 by 2, which is 20, in the map? No. We add 10 to the map. Next, 2. Is 2 halves, which is 1, in the map? No. Is 2 by 2, which is 4, in the map? No. Add 2 to the map. Now 5. Is 5 halves, which is 2.5, in the map? No. Is 5 by 2, which is 10, in the map? Yes, 10 is in our map. We've found our pair, 10 is double 5. We immediately return true. For the input 10, 2, 5, 3, the algorithm correctly returns true. This is because the number 10 exists in the array, and its half, 5, also exists, satisfying the problem's condition. You'll spot this pattern whenever a problem asks you to find a pair of numbers with a specific relationship, like n and 2n, or n and n plus k. The crucial signal is needing to check for the existence of a related value that you might have seen previously, without rescanning the entire collection. HashMaps excel at this. This optimized approach achieves an big O of n time complexity because we iterate through the array only once. The space complexity is big O of n in the worst case, as our HashMap could store all n elements. Understanding when to use a HashMap for efficient lookups is fundamental. Try applying this pattern to problems involving sums or differences. If this helped, hit that like button and subscribe for more DSA insights.